Hey space friend, this is a little embarrassing. I tracked down that distress signal from last week and it turned out to just be fellow space pirates who ended up ransacking my ship. This ship has no weapons, so I think it's officially time that I built some. We're mostly going to talk about external power supplies, and then we're going to do a project that uses servos, an ultrasonic sensor, and a laser diode module to automatically fire on ships that get too close. What? You can never be too careful out here. Here's a confession. I've always been very intimidated by using external power supplies with the Arduino, and it's really hindered my progress with learning it. So if you've had the same problem, then you're in the right place because we're going to do a deep dive into them and properly understand how they work finally. The Arduino's onboard voltage regulator is limited. The 5-volt rail can only handle about 500 milliamps whenever it's powered via USB. More high-powered components like servos can exceed this limit fairly easily, which can cause voltage dips, unreliable behavior, or brownouts and resets. It's a good idea to use an external power source whenever you're using more than one servo or other high-powered devices, or when you're using something that requires more than 5 volts. Let's talk terminology. Voltage is electrical pressure and is like the pressure in a water hose. It must match what your components need, like a 5-volt servo requiring a 5-volt supply. It pushes electrons through a circuit. Current is electrical flow, like how much water is going through the hose, and is measured in amps. The power supply has to supply at least as much as needed. It's how many electrons flow through the wire every second. When you increase the voltage, more current can flow, but only if the circuit allows it. The amount of current that can flow depends on the resistance of the circuit, kind of like how wide or narrow a water hose is. Power is measured in watts, which equals voltage times amps. This gives us an idea of total load capacity. For example, if you've got 5 volts and 2 amps going to your servo, that's 10 watts of power. A buck converter is a type of switching voltage regulator. It steps down a higher DC voltage to a lower DC voltage. Simple resistors or linear regulators tend to waste extra voltage as heat, but buck converters handle this much more efficiently. It uses an electronic switch, usually a transistor, to turn on and off super fast. The rapid switching controls how much energy gets sent to the output. The output voltage is smoothed by an inductor and capacitor, which store and release energy to supply a steady lower voltage. By adjusting the ratio of on-off switching time, called the duty cycle, the buck converter controls output voltage precisely. The reason we might use one in an Arduino project is if the power source provides 12 volts, but the actual component we're using needs 5 or 6 volts. A buck converter will safely and efficiently drop the voltage without overheating or wasting too much energy. Here's a couple of safety tips with external power supplies. Servos can easily draw 1 amp or more when moving under load, but the Arduino's 5-volt pin can only power about 500 milliamps, which is half an amp, when powered via USB. Drawing too much current could cause voltage dips that reset or freeze the Arduino, damage to the Arduino's voltage regulator, or unstable and erratic servo behavior. So typically avoid powering servos directly from the Arduino's 5-volt rail. If the power supply's voltage is higher than the device's required voltage, applying it directly can damage the component. For example, a laser or a servo could burn out if it's powered by 12 volts when it only needs 5 or 6 volts. So use a buck converter to drop voltage. In electronics, ground is the reference point for all voltages in your circuit. Think of it as a 0 voltage baseline. Everything else is measured relative to it. If you have multiple power sources, like in this case the Arduino, buck converter, and servos, they all need to agree on what 0 volts means. This means that their ground wires need to be physically connected together so that they all share the same electrical reference. Practically, this could look like connecting the ground pins of all devices to the ground sign on a breadboard's power rail and then connecting a jumper wire from the ground power rail to ground on the Arduino. I got a buck converter with LCD, barrel jacks, and a power supply cord from Amazon, links to all in the description. The AC adapter is the main wall plug-in power supply that converts your home's AC power to a stable 12 volts DC output. The adapter outputs 12 volts DC, can supply up to 2 amps of current continuously, and the output voltage stays constant at 12 volts even if the load changes, so your devices get steady power. The buck converter takes a DC voltage input anywhere from 5.3 to 32 volts and steps it down to a lower DC voltage output, which is adjustable between 1.2 and 32 volts. You can adjust this using the potentiometer. How all of this works together is the AD adapter plugs into the wall and provides 12 volt DC power. The buck converter takes this 12 volt input and steps it down to the exact voltage our components need. The LCD on the buck converter helps us verify the output voltage, and the Arduino and servos connect to the buck converter's output for stable, safe power. This is the buck converter that I bought. It was $18 on Amazon. You can definitely get them cheaper, but I like the reviews this one had, and it also included an LCD to display the input and output voltage. It didn't come put together, but I was still able to do it despite being a very not handy person. The parts we have are the buck converter board. That's the piece with the screen, buttons, and heatsink. acrylic front and back panels with screen and button cutouts, assorted screws, nuts, and brass standoffs, and blue silicone caps to place over the buttons. First, peel off this protective brown film from the acrylic panels. Position the back panel that has fewer cutouts under the board. Use the brass standoffs and screws to secure the PCB to the back panels through the 4 corner holes. Place the front panels with the LCD and button cutouts over the front of the board. Secure this panel to the standoffs using the remaining screws, and then press the caps onto the buttons. To attach the power adapter, I had to buy some barrel jacks. Pop the barrel jack onto the power adapter, then we need to attach wires from the barrel jack to the buck converter. Slightly loosen the screws on both items, just enough to be able to slide a jumper wire in and then tighten them back up. The power adapter will attach to the in section and the servos will attach to the out section. The barrel jack has a positive and a negative sign by each hole, so make sure you're lining these up to the positive and negative end holes. When you have everything set up and powered, the buck converter LCD will say something like this. It'll show you an output voltage like this, which is way too high for the components we're using, and it's drawing 0 amps because nothing is consuming power yet. First, we need to adjust the buck converter to 5 volts. This one has a tiny screw as a potentiometer to adjust the voltage. It says CV for constant voltage and CC for constant current. Constant voltage is the one we're going to adjust, so make sure that light is on and adjust the potentiometer. After we set the output voltage, we can plug the buck converter into the breadboard rails, connect the Arduino, and upload our code. Since we're using 2 servos, I connected the jumper wires from the out sections to the positive and negative signs on the breadboard's power rail, then connected the servos to the power rail. For this project, we need an ultrasonic sensor, a laser diode module, 2 servo motors, and our external power supplies. First, we include our servo library and set our pins, and then we create objects for each servo. Detect range CM shows us how close something has to be to activate the laser in centimeters. Fire duration shows how long in milliseconds the laser is going to stay on when triggered. The setup starts the serial monitor so we can print our data, and we set the pin modes for the ultrasonic sensor and laser. Servo.attach is how we set the servo pins to 3 and 5. We then write the positions of each servo to start at the center position of 90 degrees. The get distance function triggers the ultrasonic sensor to send a short high pulse to start the measurement, and it multiplies that by the speed of sound in air, then divides by 2 to get the distance of the object one way. The scanning animation is how we're simulating a scanner. The function moves both servos between 60 and 120 degrees. When we write 180 minus angle, we are setting it to move Y opposite to X for a more dynamic scanning look. In the loop, we measure the current distance and then print it to the serial monitor. If something is detected closer than 100 centimeters, then the laser turns on for 500 milliseconds. Well, that's one defense system online. This orbital overkill isn't exactly battle grade, but it's better than what we started with. Let's just hope it's enough to make fellow space pirates think twice next time.